Okay, I'll get started. Wanted to begin with a few announcements related to the end of the semester and test 3. The first announcement is about completing the teacher course evaluation. I'm sure you've got emails about teacher course evaluation. Once the class gets to 80% response rate for the teacher course evaluation, then I'll credit everybody with a 1% bonus on your overall scores. So you have until, I think it's the end of next week, so April 28th, to complete that teacher course evaluation. That's very helpful to us. It's very useful to us. Second reminder. During finals week, we've got test 3. Test 3 will have the same format as test 1 and test 2. It's the same length of time. It's a 1-hour test for test 3, just like test 1 and test 2. It has the same number of concept questions, true-false questions. It has the same arrangement of fully worked out problems. There is a practice test online, and there's the formula sheet online that you might want to consult. This is the material that we're covering on test 3. It's all of the material since spring break. It's all of the material since the material that was covered on test 1 and test 2. So it covers the lectures that we did on the properties or characteristics of nature of light. That's these 6 lectures here. We talked about reflection, refraction, diffraction. We talked about making images with lenses. We talked about making images with mirrors. We talked about interference of light. We talked about diffraction of light, and we talked about the speed of light. So all these lectures here. Also covers last week's material on relativity. We had 2 lectures on that, and it's going to cover the next 3 classes on quantum physics. It's going to cover that. So that's the material for test 3. Any questions on all that? Okay. Few special announcements about the end of the last 2 classes, the last recitation that you'll have on Monday, and also the last couple of homework assignments. So the first one here, I'm actually not here and not available on Thursday. I somehow managed to do that. So I'm going to make up that class because that class is on test 3. It is part of the material we need to cover for test 3. I'm going to make it up on Friday. So how's that going to work? I'm going to just give the lecture on Zoom on Friday at noon. You may be available or you may not be available. That's perfectly fine. You may want to tune in or not tune in. That's perfectly fine. But that Zoom lecture will be recorded, and so you'll have the recording of what would have been Thursday's lecture available from noon on Friday. I have office hours on Thursday, and I'm missing my office hours on Thursday, so I've just slid my office hours from Thursday to Friday. If that doesn't work for you, of course you can just email me and make an appointment for office hours. So I'm moving the office hours to the Friday, but if you want to talk at some other time, just let me know. Just send me an email. Monday's recitation. You've had all the recitation worksheets now. So all your recitation worksheets that go into your final grade, they're all complete now. Monday's recitation will be a review for test 3. It'll be working through the test 3 practice test. So that's the plan for Monday's recitation. The final 2 homeworks. So Monday's homework, next Monday's homework, it is for credit. It covers this lecture and the Thursday that's now a Friday lecture. So that is for credit. That's homework 14. The last homework 15, is a shortened homework because it just covers the Tuesday class next week before we break up the classes. That's not full credit. You want to look through it, you want to do it because it's material that will be covered on the test, but it's not actually for credit. I don't want that to interfere with finals. Any questions on all that? I will send out an announcement and a reminder about the special Friday lecture, the absence of a Thursday lecture during the week. And I'll send out a reminder with the link if you want to tune in. It's completely up to you, but it will get recorded and will get posted after the lecture. Okay. So like last week was a whirlwind tour of relativity, this week is kind of a whirlwind tour of the quantum nature of matter and light. And actually, one thing we're going to discover is that our understanding of matter and light, we think of them as kind of different things, waves and particles, we're going to kind of unify that understanding. We'll be thinking about them in similar ways. So we'll synthesize our wave and particle understanding of matter and light. That's one thing we're going to do over the next couple of lectures. We'll also realize, though, that the true notion or true being of light and matter is much more complicated than our everyday experience of waves and particles. We like to think of matter in terms of our everyday notions of waves and particles, but actually light and matter are much more complicated. They're not simply waves and particles. That'll be another discovery we'll meet this week. Okay, specifically today's class. I want to spend a few minutes talking about what was considered the collapse of physics. The collapse of physics, collapse of capital physics, happened more than 100 years ago, 120 years ago. It was the collapse of the physics of mechanics, electricity, and magnetism, and heat. It was a collapse because things were found out, things were discovered, things were observed that didn't fit into the theories of mechanics, electricity, magnetism, and heat. Two of the key things related to the collapse of classical physics. One is a topic called black body radiation, so we're going to talk about that today's class. The other one is a topic called the photoelectric effect. We're going to talk about that in today's class. In black body radiation, a famous scientist from over a century ago, Max Planck, hypothesized that electromagnetic energy, like the energy in electromagnetic waves, comes in packets. That was the outcome of black body radiation. Photoelectric effect, another famous scientist, you all know, Albert Einstein, he hypothesized that electromagnetic fields themselves come in packets, these things we call photons. So we're going to focus a lot in today's class on black body radiation, photoelectric effect. What is black body radiation? What is photoelectric effect? Why did it unleash this new physics, this new world in which energy in electromagnetic fields comes in packets, and this new world in which the electromagnetic fields themselves are in packets or quanta or what we call photons. Okay, so let me just remind you of classical electromagnetic waves, because we talked a lot about classical electromagnetic waves, because we talked about how classical electromagnetic waves are created and how classical electromagnetic fields, oscillating electromagnetic fields, maintain themselves and travel through space. In a classical electromagnetic wave, and here's one that's traveling from left to right, it's got an electrical field in it that's oscillating up and down in orange. It's got a magnetic field in it that's oscillating to and fro in green here. It's carrying energy, it's carrying momentum, it's traveling at the speed of light. That's our classical wave. Its electrical field, its magnetic field, they can take any values whatsoever in a classical electromagnetic wave. The electrical field could be 1 Newton per Coulomb, just to pick a round number. It could be 10 newtons per Coulomb. It could be 1,000 newtons per Coulomb. It could be any number whatsoever. So the electromagnetic fields in a classical electromagnetic wave are what I would say are continuous. They're allowed to be any value, any size whatsoever. No restrictions on their size. The energy and the momentum that a classical electromagnetic wave can carry as it travels from one place to another place, that also can take any value. The energy can take any value it likes. The related momentum could take any value that we like. So the energy, just pick round numbers again, it could carry 1 joule per square meter per second. It could carry 10 joules per square meter per second, 100 or 1,000 joules per square meter per second. There's no restrictions whatsoever on the amount of energy, how big, how small the electromagnetic field can carry. Okay, really. In that setting, classical physics collapsed. Okay, so as I say, classical physics was what we call classical physics is our knowledge, our understanding of mechanics, what you talked about in Physics 211, that's part of classical physics, electricity and magnetism, what we talked about in the first half of the semester up until we went off on spring break, and then finally heat. That's the other part of classical mechanics. And that was physics up until the beginning of the 20th century or the end of the 19th century. That physics was unable to explain the revolution in space and time that we talked about last week. That physics was unable to explain the revolution in quantum physics that we're talking about this week. So that's what broke classical physics. Relativity from last week, quantum physics from this week. It was, as I mentioned, Max Planck, Albert Einstein, who developed a new mechanics to replace classical mechanics. They developed a mechanics that's called quantum mechanics to replace classical mechanics. And it's the mechanics that we have to use, that we have to deploy to understand matter at atomic scales. So to understand atoms and molecules and subatomic components of atoms and molecules. Because it was the early 20th century, that's when all this happened. Because that was kind of the time of modern art and modern literature and modern furniture and modern architecture. They just called it modern physics. So this is modern physics. So the last 2 lectures last week on relativity are what we would call a part of modern physics. These 2 lectures, today and not Thursday, Friday, that's part of modern physics. Okay, let me show you the experiment that blew everything up. The experiment that blew everything up in classical physics was an experiment that just involves basically an old-fashioned light bulb. So here's a big, large, old-fashioned light bulb. It's an incandescent light bulb. Incandescent light bulbs have a thin metal wire in them. You pass the current through the thin metal wire. The thin metal wire gets really hot. The thin metal wire glows because it's so hot, and that's how you get your light. It's really inefficient. We don't do that nowadays, but This is what led to the collapse. The humble incandescent light bulb led to the collapse of classical physics. Okay, so let's look at this. I'm going to switch it on. And I'm going to adjust the current that's flowing through this filament in the light bulb. You can't, especially if you're back, you're never going to see the filament. I can't even see it here. But there is a very thin filament in this evacuated tube here, and we're going to start passing current through it. And we're going to start low, because I don't want to break it. I've put 10 volts across it right now. So it's some current corresponding to 10 volts. And now I've gone to about 20 volts. So hopefully you can see it glowing a little bit. There's a nice, I think it's kind of a nice orange color. Might decorate with that. So it's starting to glow, and it's glowing because we're passing a current through that's dissipating power in the filament, that's warming up the filament, and it's getting really rather hot. It would burn you if you touched it. It's glowing hot, and it's glowing a sort of reddy orange. I'm going to go up another 10 volts. It's brighter, isn't it? It's definitely brighter. And I would say it's gone from orange to a sort of orangey yellow. Go up to 40 volts. Now it's even brighter still. It's really getting quite bright. And I would say it's more yellow than orange now. We'll go to 50. Brighter still. It's getting almost wider now. And then I guess walk up. I can't remember what the maximum Mohammed told me not to go beyond, but we'll just see. It's getting pretty white now. It's pretty bright, I think. It's getting even bright. I'm up to 70 now. I don't know if that's too much. Let's go further. 80. I can barely, from here I can barely look at it, but it is really white, bright. 90. Still brighter still, and I'll go up to 100 just for fun. And that is, it seems to me, extremely white and extremely bright. It's like the sun now. I'm going to turn it way back down, and we just see it die away in intensity, and we see it change in color. Especially, look, as I turn it off here, you see it sort of go. I can barely see it now because I was looking at it, but I believe it's sort of reddish now, and then it fades away. It actually fades away into the infrared. We can't see visible light from it now, but it is radiating in the infrared. Okay. Well, that humble incandescent light bulb, as Lady Gaga says, that was the end of classical physics. It could not be explained by classical physics. Let's look at how that works. Let's look at how Max Planck also solved this problem of understanding this radiation. So the solution to the problem with the incandescent light was that electromagnetic waves that were emitted, the visible light, the other light that was emitted is emitted in packets. And his idea was that electromagnetic energy, electromagnetic fields, the energy they carry is emitted and absorbed in packets. And he got a Nobel Prize for that. Okay. So I want to introduce this topic of black body radiation. So the lamp is kind of an example of black body radiation. It's the continuous radiation that's emitted by an object. And it was very clear that filament emitted continuous radiation, continuous meaning sort of continuous in the spectrum of colors. When we passed a lot of current through it, and we made it very hot, and it glowed very brightly. So it's emitting continuous radiation. Another example of a black body, famous one, you've heard of this, is the sun. The sun is a black body that radiates black body radiation, radiates a spectrum of radiation that we just named black body radiation. Just to give you an idea, the sun's temperature is about 5,000, the surface, about 5,000 degrees Celsius. Obviously the sun is big, it's 10 to the 30 kilograms. It's some massive ball, sphere of basically hydrogen. That hydrogen is made of protons and electrons. So it's actually a vast plasma or sea of electrons and protons. Those electrons are moving around wildly with their random thermal motion at 5,000 degrees Celsius, and they're radiating. They're radiating electromagnetic radiation, and that's the source of the sun's light. That's the source of the sun's black body radiation. So that's what really is going on, and of course that's important to us because that radiation carries energy from the sun that supports life on Earth. It enables plants to grow, it enables us to eat the plants and eat the animals that eat the plants, and we all survive because of the sun's black body radiation. So it's an important topic. This is the spectrum of black body radiation from the sun. So let me spend a few minutes on, or a couple of minutes on this graph. Horizontally is the wavelength of the electromagnetic radiation. So that's the horizontal axis here. Vertically is the intensity of the radiation. So that's in joules per second per square meter. That's how we measured the intensity of electromagnetic radiation. And down here, this is wavelength in nanometers, the size of one complete cycle of the wave. That's how we measure the wavelength. The black line is a theoretical line for a perfect black body at the temperature of the sun. So that's this solid, thin black line. If the sun was a perfect black body, it would have a spectrum of electromagnetic radiation that would look like that black line. No body's really a perfect black body, but the sun is pretty close to a perfect black body. In yellow here, this is the radiation that is arriving at the Earth, at the upper atmosphere of the Earth. So that graph now in yellow, that looks pretty close to, not exactly, but pretty close to the black body spectrum. So the sun is very nearly a perfect black body. Interestingly, down here in red, this is what radiation gets to us at sea level, at ground level. So some of the radiation, depending on the wavelength of the radiation, can get through the atmosphere. Some of the radiation can't get through the atmosphere. Different gases in the atmosphere, water vapor, for example, famously carbon dioxide, for example, would absorb the radiation at certain wavelengths. Other regions, the atmosphere is like an open window and everything pours down through the atmosphere to us at ground level, at sea level. So you see holes cut in the black body spectrum of the sun. You see some holes due to water vapor here. You see holes due to carbon dioxide over here. That are where the water vapor, the carbon dioxide, is absorbing the solar radiation at those wavelengths as it tries to pass through the atmosphere. Here is a similar graph. Again, it's wavelength horizontally for the electromagnetic radiation. Its intensity, it would be in, say, watts per square meter, or joules per second per square meters vertically. Here, indicated by this rainbow, is the wavelengths of visible light, from red light to violet light, with the longest wavelength over here, the shortest wavelength over here. And here in green, blue, and brown are three theoretical black body spectrums for three different temperatures. So remember the sun, what was the sun at? 5,200 Celsius. These three graphs are for somewhat cooler temperatures, a bit cooler than the sun. They're for 4,000 Kelvin, that's the brown. They're for 3,000, that's the blue. They're for 2,000, that's the green. So these are warmer than the hotter than the incandescent light that blinded me, but they are a bit cooler than the sun. notice a couple of very interesting features about black body radiation here, black body spectrum here. Let me just point the two of them out. The most obvious one is that as you increase the temperature, and we saw this with the incandescent lamp, and we can see this on this plot here, as you increase the temperature, the brightness, the intensity grows. The brightness intensity grows really, really rapidly. You see, we've just from 200 Kelvin to 4,000 Kelvin. It's 2,000 Kelvin to 4,000 Kelvin. We just doubled the temperature, but we dramatically changed the amount of energy that's radiated. The energy goes as the fourth power, the intensity goes as the fourth power of the temperature. So if you double the temperature, the intensity is going to go up by 2 times 2 times 2 times 2. That's the fourth power of the temperature. That's 16 times by a factor of 16. So from green to brown, we double the temperature, we increase the intensity by a factor of 16. That's a big factor. It's called Stefan-Boltzmann law. Another important feature that's shown on this graph, think about the peak wavelength. So if you're looking at the incandescent lamp, you know, when we saw it glow red, that was kind of the peak wavelength. That's where the largest intensity of light was. When it was glowing yellow, say, then yellow would have been the peak wavelength. That's where the largest amount of energy was radiated in black body radiation. You notice the peak? The peak is going for a walk. The peak is walking from long wavelength at 2,000 Kelvin. So it's way over here in the infrared. It's walking to 3,000 Kelvin. It's less than a micron, so it's still infrared, but it's near infrared. It's getting near the visible light. And then finally, for 4,000 Kelvin, we're approaching, the peak is very close to red light. So the peak wavelength changes as the temperature changes, and there's a law for that too. It's called the Wien law. It's written upstairs here, very compact, simple law. Just says that the product of the temperature of your black body and the peak wavelength from your black body radiation, so that's T times lambda max, is equal to this constant, a number. And so that's a formula that describes the kind of the spectrum of black body radiation. It's telling you where the peak of the black body radiation is. So those are two features that are important. Well, yeah, I wanted to just give you a final example of black bodies. We talked about the incandescent lamp. That was one we could demonstrate where we could change the temperature. We talked about the sun. We couldn't change the temperature of the sun, but we could appreciate it. We talked about the theoretical calculation of the black body radiation for different temperatures. You and I, we're basically imperfect black bodies. We are also radiating black body radiation because we're at some temperature. We're at about 33 degrees Celsius, and at 33 degrees Celsius you also radiate black body radiation. Now we're not all sitting in class glowing because the radiation that we're emitting is not in the visible region. It's at a much longer wavelength region that's in the far infrared region. So we are radiating, we are like the sun, like the incandescent lamp, we are black bodies. It's just we don't see visibly electromagnetic radiation. If you calculate the wavelength of our electromagnetic radiation, let's calculate where it peaks at. That'd be a fun thing to do. We can use the Wien law. So we're going to use this law here, that the product of the temperature of the black body times the maximum wavelength that it's radiating at is this constant. We're going to use this law here, we're going to apply it to each of us, knowing the temperature that we're at. We're at about 33 degrees Celsius. You know this better than I. 33 degrees Celsius, we have to be a little bit careful for the Wien law in this constant. You have to use Kelvin as your units of temperature, not Celsius as your units of temperature. So to convert from Celsius to Kelvin, we add 273. to the temperature in Celsius to make the temperature in Kelvin, so it becomes 306 degrees Kelvin. Remember, Kelvin is an absolute scale. It starts with 0 at the lowest possible temperature. The Celsius scale is not an absolute scale like that. It can be negative or positive. It was just defined by, ice, the temperature of freezing water into ice, or melting ice into snow into water was 0 degrees Celsius. Anyway, so we've got to we're going to use this law. We're going to rearrange it. Lambda equals this constant divided by the temperature. We're going to plug in the temperature of you and I in Kelvin, 306 Kelvin. And if we carry out the calculation, we find that the wavelength that we radiate at is 9,400, the peak wavelength is 9,470 nanometers. That's about a 9.5 microns, and that's in the infrared, and that's why we are glowing. If you had infrared goggles, you'd see all of us in the room glowing. You'd see if all of us glowing with a peak at this wavelength of about 9.5 microns, but because we don't see it visible. Okay. Well, that's all well and good, but the black body radiation led to what's called the ultraviolet catastrophe. It sounds to me like catastrophizing, which I can't really say, but it was considered a catastrophe in physics because it was the collapse of classical physics. So why was this catastrophe a catastrophe, first of all, and why was it an ultraviolet catastrophe? That's like making it even more of a catastrophe. Let's just make it an ultraviolet one. So here, this slide is about the classical theory of black body radiation versus the experimental observation of black body radiation. So there's a few remarks over here on the left-hand side I'll go through. There's a plot over here on the right-hand side. It's the same plot of wavelength horizontally versus intensity vertically. So it's the same plot. And on here in blue is the black body spectrum that you would measure from the sun or from a human or from the incandescent light that depends on temperature. Its peak depends on temperatures. Its intensity depends on temperatures. So that's the observed black body spectrum. Here's the theory based on classical physics. This red line here. Well, at long wavelengths, the theory is actually really rather good. At long wavelengths, the red line, the theory, and the blue line, the data, the observations, are in agreement. And if we kept this graph going, we'd see they're in extremely good agreement at long wavelengths. So that's the good news. The bad news is that at short wavelengths, the theory is terrible. You see it, let's imagine walking from the theory is really good, the theory is really good. Oh, it's not quite so good now. It's getting worse now. It's getting really bad now. Big differences between theory and experiment. If you kept going on doing that, if you went to really, really short wavelengths, let's imagine going to, almost zero wavelength, really shortest wavelengths. What does the theory predict? The theory actually predicts infinite amount of radiation at short wavelengths. What does the experiment tell you? The experiment tells you that you get no radiation at the shortest wavelengths. So could you be more wrong with your theory about your experimental data? I don't think you could be more wrong if you predict that there's an infinite amount of radiation emitted at short wavelengths and you observe that there's zero radiation emitted at short wavelengths. So that's why we hype it up as the ultraviolet catastrophe. So, Max Planck came up with a solution to this problem of the ultraviolet catastrophe. And his solution is that the electromagnetic radiation that's emitted by the black body is emitted and also absorbed in packets. It's emitted in packets of energy. So you can't just emit any energy you like. You have to emit energy in packets. That's the key to his solution to the ultraviolet catastrophe. The other part is that the size of the packets depends on the frequency or the wavelength of the radiation. So we'll see in a moment that, depending on your frequency, depending on your wavelength, you have bigger or smaller energy packets. So that's the key ideas that Max Planck added to the theory. In this plot here, now the blue line is the new quantum theory of Max Planck. The red line is still that old red classical theory before quantum physics. So by adding this idea that you can only emit and absorb electromagnetic radiation in packets, and that the size of the packets depends on the frequency of the wavelength of light, then you can turn this disastrous classical theory into this very successful quantum theory. So what's the key idea? So the bullets have to do with the key idea. So firstly, electromagnetic radiation is emitted in packets, in energy packets. It's absorbed in packets, energy packets. What's the size of the packet, you might ask, right? The size of the packet depends on the frequency of the radiation. The size of the energy packet, so E is the energy packet, is equal to the frequency of the electromagnetic radiation times a new constant. Its symbol is H. It's what we call Planck's constant. It's this number here, 6.6 times 10 to the minus 34 joules a second. Or you can write it in another energy units, 4.1 times 10 to the minus 15 eV seconds. So this is the recipe. No, so there's two parts of this. There's the idea of the packets, energy packets, but then there's the recipe for how big the packets are. And key is the fact that the packets depend on the frequency. That means that a black body radiation at any particular frequency is no longer, the energy is no longer continuous, no longer smooth. No longer can you have any energy you like for black body radiation at a particular frequency. That energy has to come in packets, in quanta. So you could have, at a given frequency, you could have a black body radiation of Planck's constant times the frequency. That would be this number n equals 1. Or you could have this number equals 2, and you could have 2 units of h times s, or you could have 3 units of h times s. But you've got to come in these packets. So that's a fundamental change, that no longer is the energy at a particular wavelength the smooth, continuous thing, classical thing. Now the energy at a particular wavelength is a discretized, packeted, quanted thing. And these are the packets. The important thing about this is maybe these last 2 bullets here. At low frequencies, so let's take low frequencies as one extreme. Low frequencies is long wavelengths. At low frequencies, long wavelengths, classical theory was successful. At low frequencies, long wavelengths, the energy packets are tiny, very, very, very small. They're minuscule. And so the fact that energy comes in packets at low frequencies, long wavelengths, is immaterial. There are packets, it's not continuous, but it's essentially continuous, and so it matches classical theory. At high frequencies, what happens at high frequencies? At high frequencies, the packets become bigger and bigger and bigger. They get really big. And at high enough frequencies, the size of the packet is so big that that hot body, like the incandescent lamp, or like you, or like the sun, can't radiate even one packet, one quantum of that light. And so that cuts off, that literally stops the radiation at high frequencies, short wavelengths, and that causes the theory to tip over and give the result that at the very highest frequencies, i.e. the very shortest wavelengths, you don't radiate. And you don't radiate because you can't release these packets, energy packets. Okay, this slide, I won't go spend a lot of time on it because it's one calculation done 3 times, but it's just an example, an illustration of these packets and the important features of these packets. So in this slide, we're asked to calculate the energy in electron volts of a photon. It's one of these packets with wavelength 5 centimeters. So 5 centimeters wavelength, that's kind of a microwave. So when I cook dinner, I'm using the microwave. That's about 5 centimeters wavelength. Let's find out what energy packet that is. That would be interesting. When I'm cooking dinner, I could know how many EV I'm cooking with. Visible light, that'd be interesting too. You know, we look around us, we see all these things. How big is an energy packet? You know, is it 50 joules? Let's find out how many EV it is. And then finally, X-ray. When I go to the dentist, what is the dentist bombarding me with? What energy is the packets of electromagnetic radiation that's X-rays? So 5 centimeters is microwave, 500 nanometers is in the visible region, and 5 nanometers is in the X-ray at the dentist. Okay, so if I want to calculate the energy of one of these packets, the microwaves, the visible light, or the X-rays, I first want to calculate the frequency from the wavelength. So that's just going to be my first step. And that's just that equation that we met for waves a long time ago, that the speed of the wave, in this case speed of light, is the product of the wavelength and the frequency. So I'm just going to use, in each of these 3 examples, look, there's A, B, and C for the 3 cases here. I'm just going to start with the relationship between frequency, wavelength, and speed. So speed of light equals frequency times wavelength. I'm going to rearrange it for the frequency, knowing the wavelength. So frequency equals speed of light divided by the wavelength. If I calculate the frequency for the microwaves, it's this number here. This is 6 billion hertz. So it's a lot of oscillations per second, but actually not such a lot if you're a photon. This is 6 billion oscillations oscillations per second here. For the visible light, we did the same calculation, again divided by the speed by the wavelength. This is 6 times 10 to the 14 hertz. So this is a much, much higher frequency in visible light. It's a much, much shorter wavelength, much, much higher frequency is this value here. And likewise, if we go up to X-rays, again, same calculation, the speed of light divided by the wavelength of the X-rays, that's now 5 nanometers, we get 6 times 10 to the 16 hertz. So we got this progression here of increasing frequencies as you go from the microwaves to the visible light to the X-rays. And that's obviously what we'd expected. Now all we got to do in the second line for part A, second line for part B, second line for part C, is just multiply that frequency by this new constant, Planck's constant, to find out what the energy packet is, energy quantum is for these different frequencies, wavelengths of electromagnetic radiation. So here, E, the energy packet, is Planck's constant times the frequency. So here's Planck's constant, and here I'm multiplying it by the frequency. Here it is the result in joules. The seconds cancel out, so you just get an energy in joules. Or here it is, this is probably more convenient. This is in electron volts. So it's tiny, 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 tiny fraction of an electron volt. You know, when I think of atoms and molecules, I sometimes do think about them, I think about they're kind of electron volt kind of energy things, or maybe more. So this is really small compared to microwave energy, is small compared to typical energies of electrons in atoms and molecules. What about the visible light? With the visible light, again, we're going to multiply Planck's constant times the frequency. The frequency is much larger now. We're going to get a larger energy packet. It comes out to be 3.7 electron volts. So visible light has energy packets that are the scale of an electron volt, depending on whether you're violet or red. They're that scale. And then the X-rays are higher frequencies, and X-rays are even higher energy, larger energy packets. I think of X-rays as being the scale of keV, kilo electron volts, thousands of electron volts. This particular one is a few hundred electron volts, 370 electron volts. Okay, so this is a completely new idea. Well, it's not now. It's not a completely new idea now that it just came up with. It's a completely new idea 120 years ago when Max Planck came up with it. It solved this massive problem of the collapse of physics. Okay, want to move on to photoelectric effect. This is the second phenomenon we said we were going to talk about. I'm going to show the video for this because I think it's clearer and more likely to work. Okay. So in the video, I've got something from, this is like a time to reminisce. Remember those early lectures? I would walk around with this little guy. It's an electroscope. You could apply charge to it, and the needle would deflect. And so I'm going to use that. In the video, and I could do it here, I could charge up the electroscope. I could apply some charge to the electroscope. The photoelectric effect involves shining light onto a metal surface. So here's the metal surface at the top here. We're going to shine some light onto it. And in the photoelectric effect, the discovery was that that light that shines on a surface can liberate, literally boil off, liberate electrons from the surface. It's really a remarkable effect. And you're going to see in the video my assistant shining just a regular old flashlight to try and liberate electrons. That's this light here. And this device here, this is also a light. It's maybe a bit hard to see. It's hard to see why. This is an ultraviolet light. Right now, you're like you're on the beach. I'm sort of bathing you in ultraviolet. So we're going to use this guy here. Okay. So here I am charging up the piece of plastic pipe that I found laying around with some cat's fur. And I'm going to apply that charge to the electroscope. And so I'm kind of rubbing it on that metal surface. That metal surface is zinc, by the way, that we'll meet in an example later on. So I've charged up the electroscope, and then it looks like I've gone for a tea break, and here I come. Here I'm not going to use the flashlight. I thought I'd use this desk lamp. It's much brighter. That was a special desk lamp we got it behind us. It's extremely bright desk lamp. I'm going to use that. And then I've also got this little lamp that I introduced that is not that bright, but it's an ultraviolet lamp. It's producing high frequency, short wavelength electromagnetic rays compared to the desk lamp, which produces longer wavelength, lower frequency electromagnetic waves. No doubt the desk lamp is more intense. The ultraviolet lamp is less intense. Look, I'm shining the desk lamp on the electroscope. Nothing changes. There's charge sitting on the electroscope, and it just sat there. It didn't care about being bathed in regular old desk lamp light. Now I'm going to switch on the ultraviolet light, and I'm going to shine that. Look at that needle. What's going on there? What's going on there? When I shone that ultraviolet light on that nickel, the electrons, or some of the electrons, the excess charge in the nickel, were liberated. They literally leapt off the nickel sheet, and that's the photoelectric effect, that with light of sufficient sufficient frequencies, sufficiently short wavelength, you can literally liberate or release electrons from a metal. It's a fantastic effect. Okay. Somehow got disorientated here. What am I doing? Present. Well, we met Albert Einstein, not literally, we met Albert Einstein last week. His work, we're meeting Albert Einstein this week also. His work on photoelectric effect. Because, you know, whilst it's a wild and interesting effect that you can liberate electrons from a metal, it could not be explained. The features, properties, characteristics of it could not be explained with classical physics. It was another great collapse of classical physics. And so we're going to see how Albert Einstein rescued us from this collapse of classical physics with extending Planck's idea about packets of energy in electromagnetic radiation. Okay, so this slide shows us a typical photoelectric effect apparatus or photoelectric effect experiment. That's over here on the right-hand side, and I want to explain that. It also, in the text here, it describes how the photoelectric apparatus works, but it describes some of the findings, the characteristics that came out of this experiment. And it was these findings, these discoveries that couldn't be explained with classical physics, had to be explained with quantum physics. So that's the importance of this. So let's take a look at this setup here. So here's a source of light on the left-hand side. This is a beam of light in blue traveling from left to the right. It strikes a metal surface, maybe a zinc or nickel or whatever this was, metal surface over here. We said that that light can literally liberate electrons from the surface. It can kind of throw them off, release them from the metal. Here we see a couple of electrons flying off. In the apparatus, those electrons are collected on this other metal surface through which the light beam passed, called the collector. So here's the emitter, here's the collector. And you can study the photoelectric effect in this setup, right? You can study it because you can we could change the color of the light, which is changing the wavelength, the frequency of the light. You can measure, this is the clever bit about it, you can measure the energy, kinetic energy of the electrons that get released. If you apply a voltage between the collector and the emitter, you can create a potential hill, electrical potential hill, not gravitational potential hill, electrical potential hill that the electrons are going to have to climb up to get to the collector and create a current. So if you create that hill and you sort of inch up that hill, less and less electrons that are released can get up the hill. And if you keep driving up the hill, you can figure out what are the most energetic electrons that are released from the collector, released from the emitter, and can get to the collector. So you can actually measure the maximum kinetic energy of the electrons based on the fact that only the maximum kinetic energy electrons can climb the electrical potential hill, and by the height of the electrical potential hill that stops the flow of electrons, the collection of electrons, that tells you the maximum kinetic energy of the emitted electrons. So that's a very important feature of photoelectron emission in the photoelectric effect, is that what is the maximum kinetic energy of the electrons that you get based on what is the color, the frequency, the wavelength of the light that you shone on the metal. So that's sort of, I just showed you in the video the idea that you shine light and you get electrons liberated. But really you want to know, well, how does the electrons change when you change the intensity of the light, change the wavelength, the frequency of the light? How does the energy of the electrons change when you change the intensity and the frequency and the wavelength of the light? You want to know all those things. Out of that came a really surprising discovery. So that's this two unexpectedly's here. There's an unexpectedly here, unexpectedly here. The first unexpected thing is, supposing I've got a lamp and I go and get a brighter lamp. And then I go and get another even brighter lamp. And then I get a super bright lamp. That doesn't affect the kinetic energy, the maximum kinetic energy of the electrons that are emitted. You get the same maximum kinetic energy whether you use a really dull lamp or use a really bright lamp. It doesn't matter the intensity of the light that you're using. It doesn't actually affect the kinetic energy of the electrons. So that's a really, really strange thing, because you would think like a brighter lamp, there's more intensity, there's more joules per second per square meter. I've got to get higher energy electrons. But no, you don't get higher energy electrons. Whether it's a dim lamp or a bright lamp, you get the same maximum energy for the electrons. What does change the maximum energy of the electrons is the wavelength or the frequency of the light. You get higher energy electrons with higher frequency light, shorter wavelength light. You get lower energy electrons with longer wavelength light, lower frequency of light. And so it's the frequency and the wavelength that affect the kinetic energy of the electrons. Actually, it's even the frequency and the wavelength that determine whether you even emit photoelectrons. So if you have too low a frequency or too long a wavelength, you won't even emit electrons. You can't even liberate electrons from the metal. You need a certain minimum frequency. You need to be below a certain maximum wavelength to emit the electrons. And then if you continue and increase the frequency or decrease the wavelength, you'll get more and more energetic electrons liberated. So there's a very important discovery, and classical physics could never explain that. This is just to make it a little bit more quantitative. I just replaced the bullets with this. This is like my notebook from when I was 100 years ago doing the photoelectric effect. I'm plotting the frequency of the light horizontally here. So that's the F. And I'm plotting the maximum kinetic energy of the electrons vertically here. That's the KE. I'm plotting my results for 3 different metals: sodium, aluminium, copper. And here are the results. These 3 lines, the green, the red, the blue line for the 3 different metals. What are these lines telling me? Okay. Firstly, let's just take the blue line to start with, sodium. If my light has a lower frequency than this frequency here, called the cutoff frequency, you can't emit electrons. So you've got to be at the cutoff frequency or above to emit electrons. Once you get above the cutoff frequency, look, you are emitting electrons, and the kinetic energy of the electrons that are emitted increase with the frequency of the light. And so that's the basic feature of the photoelectric effect. The cutoff frequency also depends on what particular metal. So in this little picture here, sodium has a cutoff frequency that's relatively low. In green here, copper has a cutoff frequency that's relatively high. So if you had light that was a frequency between sodium's and copper's cutoff frequency, somewhere in here, it would cause photoelectrons to be released from sodium, but wouldn't cause photoelectrons to be released from copper. So metals are different. They have different, they'll give up their electrons more or less easily. That is described how easily or difficultly a metal like sodium or copper will give up their electrons. It's described by a quantity that's called the work function of the metal. It's given this symbol phi. And here's a table of work functions. So if we look at this table here, the work function for sodium is 2.4 electron volts. The work function for copper is 4.7 electron volts. Copper's is about twice the size of sodium's. You see on here, the cutoff frequency for copper is about twice the cutoff frequency for sodium. So this is just an indication of that. Where else am I going? Okay. This is Einstein's explanation of how this all works. So we've looked at the experimental data, that you need a certain frequency to emit light from a metal, and it depends on the metal. So there's a cutoff phi. That's also an energy. So the first thing is you've got to, with your photon, bring in enough energy, h times the frequency, to liberate an electron in the metal, and that means giving it enough energy to overcome the work function, the phi. If your energy of photon is larger than the work function for the metal, then that extra bit of energy that the photon brought in can be carried off as kinetic energy of the electron. And so the maximum kinetic energy of the electron is basically the difference between the incoming bullet, the photon, its energy, and the energy that you need to use up to liberate the electron from the metal. What's left, what energy is left from what was carried in by the photon, is given to kinetic energy of the electron. And so that's this equation here. This is Einstein's equation for the photoelectric effect, that the kinetic energies of the emitted electrons can be up to a value which is the h times f, that's the energy carried by the photon, less the energy that we need to use up to release the electron. That's the work function here. So this is based on Einstein's description, on Einstein's idea. This is the equation that describes the photoelectric effect. And this equation says, right, it's not the intensity of the lamp that counts, the brightness of the lamp that counts. It's the color, the frequency, the wavelength of the lamp that counts, because that's going to determine the energy of the photons and determine whether you can kick out an electron or you can't kick out an electron, and determine how much maximum energy that electron can have if you could kick it out. Okay, so this is just a graphic. I don't really know the great point of it, but I put it in here. It's a graphic of the photoelectric effect. Here's the metal. This block of material here, sodium metal. Here's the light, the beam of light here. The classical kind of macroscopic view of this is that the beam of light is this wave of electromagnetic fields. The metal is sort of some continuous, smooth container of electrical charge. To understand the photoelectric effect, we've got to think about it from this microscopic quantum perspective. That beam of light is a collection of photon bullets that are striking the metal. That metal is contained with discrete individual electrons. What's happening here is collision between the individual photons and the individual electrons to release them from the metal. It's all based about photon hitting an electron, not about a smooth electromagnetic wave and a metal containing just smooth arrangement of charge. Okay, quiz. Oh, I didn't publish it. Okay, I'll give you a minute to think about that. I'm not going to give you very long because of my own poor time management, so I'll just, make you pay the penalty for that. Because I'll then try and get in a quantitative example on the photoelectric effect. You know, if you're a few minutes late putting in your answer to this question, that's fine. Okay, so what was the question? Photoelectric effect. We're asked to think about either increasing the intensity of the light that was shining on a metal, or increasing the wavelength of the light shining on the metal. And we're asked to think about whether the maximum energy of the emitted electrons, whether it grows or whether it shrinks, with those two possibilities of increasing intensity or increasing wavelength. Okay, I'm gonna move on quickly because I want to do the example for the photoelectric effect. We said that the kinetic energy is not affected by the intensity of the light. Whether it's a dim light or a bright light, if the frequency and the wavelengths are the same, you're going to get the same kinetic energy of electrons. It's the frequency and wavelength that counts when you it's the frequency and wavelength that counts in determining the kinetic energy of the electrons. The higher the frequency, the more energetic the electrons. The higher the frequency is, the shorter the wavelength of the photons or the light. So if you were to increase the wavelength, you are decreasing the frequency, you are decreasing the kinetic energy of the photoelectrons. So increasing the wavelength decreases the kinetic energy of the electrons. Okay, so just to end up with a quick example of photoelectric effect. This one is about zinc. We said that all metals have their own work function. It's kind of just like a property of each metal. It has like its density, it has a work function. Zinc, you can look up its work function, it's 4.3 electron volts. That number, the work function of a metal, is enough to tell you this cutoff frequency, this cutoff wavelength, below which, for the frequency, you can't emit electrons. Beyond which, for the wavelength, you can't emit electrons. So we're going to calculate the cutoff frequency and the cutoff wavelength. At the cutoff frequency or cutoff wavelength, what is happening? At the cutoff frequency, cutoff wavelength, your electrons are emitted with essentially zero kinetic energy. Yeah, you just liberate them, but you just got them outside the metal, and there's nothing left to give them any kinetic energy. So that incoming photon is just enough to push out an electron. So at the cutoff frequency, cutoff wavelength, the energy of the photon, that's HF, is equal to the work function, equal to the amount of energy you need to liberate the electron. There's none left to give it kinetic energy. So to find the cutoff frequency, cutoff wavelength, we just use the fact that that cutoff corresponds to the incoming photon energy being equal to the work function of the metal. So if we want the frequency, the cutoff frequency, we can just rearrange this equation. For the frequency, it's the work function in energy, it's an energy divided by Planck's constant, which is energy times seconds in units. And if we carry out this calculation, you get a cutoff frequency. If you want the wavelength corresponding to this cutoff frequency, well, that's not really about the photoelectric effect, it's just the relationship between wavelength, frequency, and speed. We can just use that old recipe here. Here's the speed, here's the wavelength, here's the frequency. We can rearrange it for the cutoff wavelength in terms of the cutoff frequency. It's just the speed of light divided by that frequency. It's about 288 nanometers. So that's in the ultraviolet. So visible light won't eject electrons for zinc. You need ultraviolet light for zinc. If you had 5.5 EV photons, supposing we've got in excess of 4.31 EV photons. Now we've got 5.5 EV photons. Of course, then we can certainly emit electrons, and after we've given up some of that 5.5 EV, we've given up 4.31 EV to liberate the electron, there's a bit left. That remainder is the maximum kinetic energy that you can give to the electron. So with 5.